Okay, let's begin. So, where am I? Where is my chat? Okay. So, you saw the flipping, or do you want to reflip again? Yes, it was rotating as I opened it up. It says heads. Yeah, homework it is. The one that happened, the last one, the last flip we had was a head. Well, actually, as I tried 3 different things, we had the first tail, which was before the class started, and then we had 2 heads, so it is a head. So we have a homework. So homework is due. Don't forget to submit it. Here is the flip. It was happening in front of those who were watching. So, I think we're good, right? I didn't cheat. It was what happened here. Now, so it is a homework. And let me put this one down. So there are a couple of things I really want to talk to you before we're going to move on with the material. So the first thing is I do want to talk about counting because it seems like there were a couple of points we might have missed and I did not emphasize them enough. So we are going to look at a very common problem of we have a bit string of size 5. So now let's talk about common mistakes. Yeah, the homework is due 10:30 a.m. today, so it's right after the class. So you need to submit it. The homework is always due the class. So here we go, bit string size 5. A couple of questions. So how many bit strings of size 5 do I have? Okay. And now here is a trap. The questions so-called like at least. So assume you have at least, I want to have at least 2 ones. How are you going to do a problem like that? I'm going to write in red saying no good. So what is no good? The no good is that. People say, I need to find the 2 spaces for 1. And then I have 3 spaces which can be whatever I want. This is looking good, but it's broken. This is red. Red meaning don't do. And now I'm going to explain to you why it is bad. So assume I'm going to first place my 2 ones over here. This is my first part, okay? And then my other part is going to do 0, 1, 0, okay? As an example, can it happen? Yes, because we said we do not care what is at other places. Question is, how is it different from saying I put those 2 ones here and then I randomly pick those one like this? Is it different or is it the same combination? I have the same bit string, correct? But it is counted inside my combination twice, correct? Moreover, now I can say, actually, I changed my mind again. It's going to be those ones I'm picking, and this one is going to be my random ones. So guess what? This combination out there is many, many times, correct? So this one counts duplicates many times. Really wrong. Don't do it. I know sometimes people want to do it because it's kind of like in our, it might make sense, correct? To think like that, but that's a wrong thinking. Never, ever, ever do it. So what I want to get from here is at least is bad. Try to rephrase to use exactly. Exactly is your friend. Exactly are much easier to compute. So in this case, we have 2 ways of rephrasing it. Phrase number 1, solution, good solution number 1. So in order to have at least 2, I believe, yes, at least 2 ones, is the same as saying exactly 2 ones or exactly 3 ones or exactly 4 ones or exactly 5 ones. This one is good, but kind of long. So for exactly 2 ones, I can easily say that I need to pick place for my 2 ones, and the others must be zeros. So I do not pick anything anymore. Then the next one is 3, pick 5. Sorry, 5, choose 3. 5, choose 4. Or 5, choose 5. This is going to be correct long way, but it is a correct way of thinking. This is good. This is how you should think about it. We rephrase it as exact. 2, okay, out. 2, we can think about it as all possibilities minus no ones. This is minus, yes. And again, minus 1, 1. Exactly 1, 1, yes? So let me use exactly 1, 1. So now this one, all possibilities we already said is 2 to the power 5. How many bit strings of size 5 do not have ones at all? Yes, I see 1. 1 is good. And then how many strings have exactly 1, 1? So this is your solution number 2. And if you open it up, you hopefully going to get the same number. But those are 2 good ways of thinking about it. Now, this one is a bit smaller, like by 1 term, so it might be easier. I don't care if you use 1 or 2. I really care if you use the no bad one, because this is a wrong answer, correct? This is incorrect broken logic. So you really need to do the at least. It really has to be at most. So now I want to talk about problem 5C on your discussion. I know TAs were supposed to announce to everybody, but this is a complicated problem, and this is the last one to give a try. Did somebody give it a try? Anybody else? Who tried it? Okay, well, let's check. What is at 5? So in problem 5C from the discussion, we have 52 cards. Now there are 4 suits, 13 of each. Yes. The question is, how many 4-hand cards have at least 1 10 and exactly 2 diamond cards? So, do I have a bad thing here in the way my question phrased? Should I rephrase it? Yes. So what word we do not like? We do not like the at least, correct? So now let's try and think how can we rephrase it. So actually what I want here is I want here at least 110. My options are exactly 110 and exactly 2 diamonds. My option 2 is exactly 2 10s and exactly 2 diamonds. My other version is exactly 3 10s and exactly 2 diamonds. Question: can I have exactly 4 10s? No, because I cannot have 4 10s because I only have space for 4 classes, but I only going to have 1 diamond, correct? And I do need exactly 2 diamonds. So the 4 option is no possible, okay? Not a possible option. So now let's try and think what works for us for case 1, 2, and 3. So and here we go. Let me check the N. Yes, Justin is saying, could you take away 1 diamond and use 10 diamonds. So if you have a queen of diamond and 10 of diamonds, those are 2 diamonds, correct? So Justin points us to a cool thing here. We have good 10s, which are not diamonds, but we also have 10 of diamonds, which is kind of a special case. Do you agree? Because the 10 of diamonds supposed to count for the 10, but it's also supposed to count for the diamond, correct? So this is where we're going to separate it. So we will note that 10 of diamonds is special. So we will need to have a special case for her. So one option for me in here is no 10s of diamonds, because 10 of diamonds will have to have a special treatment. So how can I get exactly 1 10 and exactly 2 diamonds and not use 10 of diamonds at all? No 10 of diamonds. How can I get it? So how many possible 10s do I have? If 10 of diamonds is impossible, I only have 3, correct? So this is picking up 10. 10, not, I'm going to call it D, okay? Not diamond. Then I can pick, I need to pick 2 cards of diamonds. Now, it's 2 out of how many? If my 10 of diamonds is not allowed. So it is out of 12 because 10 of diamonds is extracted from my possibilities. So now I have, these are 2 diamonds, not 10. And then finally, how many more cards do I need? 1. And how many cards do I have to pick from? So now this is where we need to count how many we still have left, how many we still can use. So let's think. Can I pick a diamond? This last card, can I pick a diamond? No. Can I pick a 10? No. So how many cards are bad cards, the ones I shouldn't touch? Okay. 16 are bad. I agree with that. So 52 minus 16 is 36. And this is my option out here. Okay. Now I need to look at a special case. I have 1 10 and this 10 is a lucky diamond. So in how many ways can I pick my 10 of diamonds? This is not probability, correct? This is like, in how many ways can I pick just that specific card where there is no real pick, correct? I really have to grab it. So it's 1, correct? So it's literally like taking this special 10 of diamonds. So this is my 10 of diamond pick. Now, how many more diamonds do I need? 1. And how many diamonds I have to pick from? 12. Good. And now the last but not least, how many more cards do I need? 2. And how many good options do I have? Correct. It is still 36 because I cannot pick any more diamonds and I still cannot pick any more tens, correct? So tens and diamonds are eliminated. Now, I think this is good enough of a hint for this question, and now you should be able to finish it up for group work. What do you think? I just going to hint you that you're going to have a special case here. And I'm going to, let's look at this last case. And the very last case, we have exactly 3 tens and exactly 2 diamonds, but I only have 4 spaces, correct? So in order to have 2 diamonds, what can you tell me about this case? What about, do I have 2 cases or just 1 case? We must have the 10 of diamonds, correct? So for this case, must have 10 of diamonds. There are not going to be cases in this case. You must pick it, okay? So I'll let you finish it up on your own as your discussion. We will do more of those examples, bring more questions for our review section on Monday. And I'm ready to move back to chapter 7 unless there are clarification questions you want to ask. Now, after the class, I'm going to make the quiz as a like 0-point quiz. Still try to take it. It has more like, you know, questions. There's like 4 questions from counting. You should try and do out there. Hopefully you should be able to do it pretty easily. And then we're going to have our review session on Monday. So bring in more questions and try to finish up the discussion. Make sure you know how to do the questions. However, there are tons of other problems I didn't put on this like discussion sheet. It doesn't mean that they might not, like they're not going to show up. It's just, again, it's a review and there is that much you can put for you to do in like 50 minutes of the discussion, correct? So there are lots of other questions to play with. The best way to practice is to do as many questions as possible from the textbook, including homework and discussions, okay? So back to our things. We have been talking about conditional probabilities the last time we talked, and you did the group work, and this was, I believe, the last thing we did. So I have a couple of videos to show you before we move on. Okay. Let me change.
Imagine a group of people. How big do you think the group would have to be before there's more than a 50% chance that 2 people in the group have the same birthday? Assume for the sake of argument that there are no twins, that every birthday is equally likely, and ignore leap years. Take a moment to think about it. The answer may seem surprisingly low. In a group of 23 people, there's a 50.73% chance that 2 people will share the same birthday. But with 365 days in a year, how is it possible that you need such a small group to get even odds of a shared birthday? Why is our intuition so wrong? Out the answer, let's look at one way a mathematician might calculate the odds of a birthday match. We can use a field of mathematics known as combinatorics, which deals with the likelihoods of different combinations. The first step is to flip the problem. Trying to calculate the odds of a match directly is challenging because there are many ways you could get a birthday match in a group. Instead, it's easier to calculate the odds that everyone's birthday is different. How does that help? Either there's a birthday match in the group or there isn't. So the odds of a match and the odds of no match must add up to 100%. That means we can find the probability of a match by subtracting the probability of no match from 100. To calculate the odds of no match, start small. Calculate the odds that just one pair of people have different birthdays. One day of the year will be person A's birthday, which leaves only 364 possible birthdays for person B. The probability of different birthdays for A and B, or any pair of people, is 364 out of 365, about 0.997, or 99.7%. Pretty high. Bring in person C. The probability that she has a unique birthday in this small group is 363 out of 365, because there are two birth dates already accounted for by A and B. D's odds will be 362 out of 365, and so on, all the way down to W's odds of 343 out of 365. Multiply all of those terms together, and you'll get the probability that no one shares a birthday. This works out to 0.4927, so there's a 49.27% chance that no one in the group of 23 people shares a birthday. When we subtract that from 100, we get a 50.73% chance of at least one birthday match, better than even odds. The key to such a high probability of a match in a relatively small group is the surprisingly large number of possible pairs. As a group grows, the number of possible combinations gets bigger much faster. A group of 5 people has 10 possible pairs. Each of the 5 people can be paired with any of the other 4. Half of those combinations are redundant because pairing person A with person B is the same as pairing B with A, so we divide by 2. By the same reasoning, a group of 10 people has 45 pairs, and a group of 23 has 253. The number of pairs grows quadratically, meaning it's proportional to the square of the number of people in the group. Unfortunately, our brains are notoriously bad at intuitively grasping nonlinear functions, so it seems improbable at first that 23 people could produce 253 possible pairs. Once our brains accept that, the birthday problem makes more sense. Every one of those 253 pairs is a chance for a birthday match. For the same reason, in a group of 70 people, there are 2,415 possible pairs, and the probability that 2 people have the same birthday is more than 99.9%. The birthday problem is just one example where math can show that things that seem impossible, like the same person winning the lottery twice, actually aren't unlikely at all. Sometimes coincidences aren't as coincidental as they seem.
Okay. How did we like the cartoon?
Yeah. So those of you who have like ever been to a party or something or talking to other people, it's pretty common to share the birthday date, correct? Although if you think about it probabilistically, it's kind of doesn't make sense. But 23 people, it's like there is 365 days, correct? So you would think using our pigeonhole principle, we need at least, correct, 366 people to make sure for 100% we do have this match. Yes? But a 50-50 chance, actually the probability of half, apparently you only just need 23, which is so much smaller, correct? Than 365. Okay, lovely. So this is one of the common, well-known paradoxes. Now, let's talk about Bernoulli's trial, which will require... Oh, did I totally kill the window? That was a mistake. Okay, let me find it again. We're going to watch another
Do you know how many planets there are? Let's make a model of the solar system. Okay, we're going to be learning about something that's called a Bernoulli trial. Okay, so we've got a nice definition on the board, so let's go through it. So it says a Bernoulli trial is an experiment in which the outcome is either a success or a failure. Okay, so in other words, it's only got two outcomes. Okay, and a classic example of this is if I flip a coin. Okay, my outcome is either going to be, oh, I get ahead or I don't get ahead. Okay, so I either get a success or a failure. Okay, so that's what a Bernoulli trial is. Okay, so another condition of the Bernoulli trial is that the probability of each outcome is independent of the results of the previous trial. Okay, so if we go back to our coin example, okay, if I flip it once, okay, probability of getting ahead is going to be the same probability as if I flip it again and again and again. Okay, so the probability of each of the outcomes is going to be independent. Okay, so it doesn't matter on how many times I've done the event. Okay, so it's just independent towards all the previous trials. Okay, and one more thing is the probability of each possible outcome, okay, is the same for each trial. Okay, so again, the probability of getting ahead is a half. Okay, if I flip it again, the probability of getting ahead again is also a half. Okay, so it's independent and it's also the same each time. Okay, so Bernoulli trials has the same ideology as just a binomial probability. Okay, so I either get a success or I get a failure. Okay, that's the main thing. So if we take a look at some of the questions here, we're going to try and classify if something is a Bernoulli trial or not. Okay, so it says determine which can be defined as a Bernoulli trial. Okay, so if we look at part A, let's take a look at the event. So it says rolling a die and recording the number that comes up. Okay, so the first thing that we know about Bernoulli trials is that the outcome's either going to be a success or it's going to be a failure. Okay, but if we look at the outcomes of a die, okay, it's actually 1, 2, 3, 4, 5, 6. Okay, so in this case, no, it's not a Bernoulli trial because, like I said, the outcomes are not just one or the other. We have multiple outcomes. Okay, so this is not classified as a Bernoulli trial. Okay, so let's take a look at part B. Okay, so the event here is we have rolling a die again, but we're going to look at it specifically. So rolling a die 5 times and recording the number of 3s that come up. Okay, so this is a little bit different sort of situation here. Okay, so we're rolling a die and we're going to record. Okay, is there a 3? Okay, yes. If there's a different number, then no. Okay, so in this case, it does have a success and a failure outcome. Okay, so in this case, yes, it is a Bernoulli trial. Okay, because the outcomes is either a 3 or not a 3. Okay, so I want you to note the slight difference there. Okay, in the next one, okay, we have spinning a spinner. Okay, numbered 1 to 8, and then we're going to record that the number is obtained. Okay, so this is very similar to my rolling the dice. Okay, so 1 to 8. Okay, if I record the outcomes, it's just going to be all the numbers through 1 to 8 instead of just a binomial. Okay, so in this case, no, it's not a Bernoulli trial because the outcomes there are more than 2 outcomes. Okay, that's the reason. Okay, looking at this one, so we have tossing a coin. Okay, so that was our classic coin example. So if we toss a coin 7 times and record the number of heads are obtained. Okay, so is this a Bernoulli trial? Yes, it is. Okay, because the outcome is either a head or a tail.
Okay, so that's a nice one. Okay, now looking at this one, okay, we're going to looking at cards from a deck. Okay, from a deck of 52 cards, we have to consider the event where we're going to draw a card 5 times from a fed deck without replacement and recording the number of red cards. Okay, so let's just have a think about what this actually is talking about. So we have a fed deck of 52 cards. Okay, and it says drawing a card 5 times. So note that it doesn't say drawing 5 cards. It says drawing 1 card. Okay, and then I'm going to look at the card, and then without replacement, okay, meaning I'm not going to put the card back. Okay, I'm going to draw another card, and I'm going to do that 5 times. Okay, and with all my outcomes, I'm going to record how many times I get red cards. Okay, so is this a Bernoulli trial? No. Okay, because the outcome is dependent. Okay, between the last trial. Okay, so if I take one, okay, without replacement means the probability the next one is going to change. Okay, so that's what it's saying when it says the outcome is dependent because the probabilities are not the same for each trial. Okay, so every time I pick a card, my probabilities will change. Okay, now in F, okay, we're going to draw a card 5 times from a fed deck again. Okay, but this time we're going to consider it with replacement. Okay, so if I draw a card, and I look at the card, and then I'm also going to put it back before I take another card. Okay, I'm going to do that 5 times. Okay, so with replacement and recording the number of black cards. Okay, so similar situation. Okay, except we have with replacement. Okay, well in this case, yes, it is a Bernoulli trial because the outcome is independent. Okay, or in other words, it's the same as the event before. Okay, because I am replacing it with the card. Okay, so we've been going through the events that classify things as a Bernoulli trial.
Okay.
Lucidchart makes intelligent diagramming easy and helps your best ideas become real. Start from scratch or get started with templates.
Okay. So why Bernoulli is important? So let the probability, so I'm going to give you a theorem. The probability of exactly k successes in n independent Bernoulli trials with p being probability of success and q equal to 1 minus p is probability of failure is and choose k, p, k, q, and minus k. Does that remind you something? Does that look familiar? This is the binomial coefficient and how we can actually apply it into Bernoulli's trials. This is why it was so important. And in the video, it was explained to you how to even determine if the problem is Bernoulli trial or not. Because if you decide it's a Bernoulli trial and you can calculate probability of success and probability of failure, there is an easy formula on how to calculate key successes in n independent Bernoulli's trials. So that can be used, for example, in flipping the coin, when I can have a head or a tail, yes, with a probability of half and half, correct? And then I can calculate. So for example, I'm going to say my success is a head. So I can ask you, what is the probability of having 5 heads out of 10 trials? And this is where you can use this formula, because you're going to choose 5 out of 10 where exactly the success can happen, correct? And then you're going to multiply it by probability of success, which is 1 over 2 to the power 5, multiply 1 over 2 to the power 5 again. So pretty much it's going to be 1 over 2 to the power 10. And this is going to be the probability. So this is kind of a combination again of probability with counting, correct? With the counting, you could have given me the 10 choose 5, right? But this gives you actual probability. Okay. Next. Definition. A random variable really a random variable is a function from the sample space of an experiment to the set of real numbers real number assigned to possible outcome So here is an example. My random variable x is going to be number of heads when I like flip a coin, for example, 3 times. So now let's calculate the value of random values. So assume my toss, my experiment, gave me head, head, and tail. What is the value of function x or variable x of head-headed table? What it needs to do is you read carefully what is my variable is. My variable supposed to give me, it's supposed to be equivalent to number of heads. How many heads do I have if I threw in head, head, tail? 2. So this value is 2. Now, random variable can be used to calculate different probabilities and so on. But by itself, random value is just a function. It's not a probability. And you just need to understand what this function is calculating, and then you can do it. So what is the value of z? Okay. What is why is it jumping on me so badly? X of hat is and X of tail hat is 2. And again, I do not have to keep on going, but hopefully you understand the idea. And now there is another thing I need to define for you. The distribution of a random variable X on a sample space S is the set of pairs R, P of X equal R for all R in X of S, where P X equal R is the probability that X takes value R. So let's go back to my exercise over here on top and my random value. So again, still same example, X number of hats, and we're still doing 3 flips. They are independent. Okay, so what is the probability of X taking value 3? Well, in order to do it, it's going to be the best for me to finish up all of my possibilities. So how many total possibilities I have here? I am throwing 3. So how many possibilities do we have? 2 to the power 3, which is 8. So let's add the missing ones. Who am I missing? I am missing head, tail, hat, which is 2. I am missing tail, tail, hat, which is 1. I am missing tail, hat, tail, which is 1. And I'm missing head, tail, tail, which is 1. I think now I have all possible options, correct? So now for this special variable, what is the probability that the value my variable takes is 3? One over 8 is correct because I have 8 options and it is 1 over 8. Okay, I'm sorry it's not writing for me, but that should be 1 over 8. And before I let you go, one more. What is my probability of getting 2? What is my probability the variable is 2? 3/8. Correct. So that's it. We're going to finish it up tomorrow. I do have a homework for you. It's going to be posted. We are done with section 7.2 and I'm going to post your homework from 7.2. So have a good day. And again, if you have a couple of minutes, you can see I'm going to write the homework out here. If not, you can go. It is going to be posted on Icon.